So, I will continue from the same discussion which we were discussing in the last session. We were discussing some of the motivations behind the performance based design, the development of this methodology actually, or rather I would say it is a technology which you can say transfer or adopt or learn through this course or introduce yourself through this course. So, I actually started discussion based on three aspects. The first one was about the role of traditional building codes, what role they play in our overall construction industry. Then the aspect of rapid urbanization, the growing needs of infrastructural facilities, and then the third one was about the seismic hazard and overall seismic hazard of the world also, as well as the seismic hazard of Pakistan. So, from all of these three aspects, we actually kind of deduced or discussed some, you can say, motivations which led us to the development of this new seismic design philosophy. Actually, this performance based approach is more general. It is primarily developed for seismic analysis and design, but this methodology itself can be applied to any other loads also. For example, currently there are a lot of efforts to extend this methodology to wind loading. So, currently if you just search for performance based wind design, you will find many reference documents and standards even which discuss about the extension of this approach to wind loading also. And the basic idea for this approach is that a decision maker sets a performance objective and engineer follows that performance objective, fulfills that performance objective, and in doing so he uses advanced analysis and design procedure. He is free to use any other approach, alternate approach, if it is approved by an authority having jurisdiction. So, if that approach is approved by some authority which is, you can say, regulating the structural design at that particular site, you are free to do that. So, it is not necessary to follow the letter of a particular building code if you are going for that alternate approach. This is the summary of this approach. Now, this can be extended to seismic design, but for other kind of loadings also. For example, in wind load, the performance objective can be that at that much return period thunderstorm or at that much level of loading of wind, I want some minor damage only in my non-structural components, or I want complete, you can say, building to remain elastic, for example, under that particular level of loading. So, the idea that performance objective is set by the client or building owner is applicable to any other loading also. So, currently we will be focusing primarily on seismic analysis and design, the use of this approach applied to seismic analysis and design. But obviously, it is an advanced topic. It is you have to go beyond the conventional seismic design approach. So, I will try to cover some of the basic topics first in first few weeks, and then we directly go to the PBD philosophy for seismic design, right. So, I will skip that discussion quickly. First, I discussed about the role of building codes, that how they provide us a shelter and using which we can just hide behind this shelter, and we avoid all those explicit questions asked by the building owners and public obviously. So, performance based design is an attempt to answer some of those questions. Obviously, we may not be able to directly give a warranty of our structural performance, but still with some more confidence, at least we can discuss with the client in some common language. Currently, if I ask you that conventional design procedure, whatever output or intended performance you might think of for your structure, can you explain that to your client? I think most of you will say no, because client doesn't care that what method you used or what analysis procedure you applied. Client just want to have an answer of this question, that will my buildings be safe or not. So, in performance based design, you can actually tell that what damage you are going to sustain for what level of an earthquake, what cracking, what yielding, what you can say concrete crushing or steel yielding you might expect at a certain level. So the performance is clear. You can directly tell this to client that if tomorrow this much level of an earthquake occur, this much repair cost you should expect, and if it is acceptable, then design is okay, right? So you are directly relating building performance with the hazard level, right? So you are cutting that all limits and rules and all those building code things from in between. Obviously they will still be remain relevant, because at least you first need a starting design, and that you can get from the conventional code based design, right? But then on top of that, you can go for nonlinear analysis to explicitly check how that design will work if this much level of an earthquake come tomorrow, right? So the first aspect was this one about building codes. So I'll skip all that detail. We discussed actually some of the limitations of conventional building codes. What are the things they are missing actually? So we know that they mostly cover the conventional buildings, low-rise buildings, and their intention is to make the engineer able such that he follows that cookbook procedure and ultimately result in a safe design, right? That intention, that implicit intention of building code sometimes may not come true. Sometimes even code compliant buildings may not perform well, or sometimes your desired performance objective doesn't match with the code's intention of performance objective. Code's intention is life safety at design level, and you sometimes might not agree with that intention. Sometimes you say that my building should remain completely operational under the design earthquake. I want to go beyond life safety. On top of life safety, I also want no damage in non-structural elements, no damage in building contents, because sometimes the contents of the building are far more costly than the structure itself. Structure is just 10-15% of the total cost of the building, right? Because for example, imagine a hospital containing very expensive equipment which is sensitive to accelerations and drifts, right? So in that case, you might set a different performance objective. For example, that I don't want any downtime. I want the building to remain completely operational or immediate occupancy, that people go out and then after an earthquake come back and start doing same things, right? So these performance objectives becomes your design criteria. And then one more thing which I want to highlight here is that building codes always allow alternate procedures. This misconception that performance based design is somehow against building codes design philosophy is not correct, because every building code contains an escape clause, mostly found in their first few chapters. Starting chapter, for example, first chapter, or the scope of for example, a particular building code, that particular section, they always mention that if you have some other alternate design philosophy which you can justify, which is more advanced than the code's design philosophy, which you can get approval from the authority having jurisdiction at your site, you are allowed to go for that option, right? So building codes allow the use of performance based philosophy for your buildings if you can justify it in front of an authority which regulates the building structural design at your site, right? So that impression that PBD is somehow against or violating the building codes is not correct. They allow, all building codes allow the use of alternate procedures if they can be justified, right? So which means that we must have a parallel legal system or legal framework associated with PBD which regulates the PBD process, and if that system gives the legal framework or legal authority at a particular site to PBD, then PBD will become an authorized legal design procedure in parallel to the code, right? And in all the other countries, in several countries actually, that system or that framework of PBD actually exists. at the building control or building authority level, right. So the second aspect was about the rapid urbanization. I actually gave you few examples also how a prescriptive or traditional building code is different from a performance oriented building code, because in performance oriented approach we directly mention the performance, we directly mention what is required, right. We don't give a cookbook type procedure to go implicitly reach that performance. We directly mention that this is the performance and you have to show explicitly that this performance is met. For example, if the performance objective which as a client I set for a structural designer is that I don't want anyone to get injured under this much level of an earthquake, right. Let us say this is my performance objective. Now the typical procedure, now the structural engineer, if he is following PBD, he have to actually prove that there will be no casualty under that earthquake. He have to design buildings such that he can explicitly show this to client, right. So now you are free to use any procedure, any modeling, any software, anything. Ultimately you have to prove to the client that there will be no casualty. So the normal procedure would go like this. You will conduct a detailed nonlinear dynamic analysis, and for that you have to first construct a nonlinear structural model, a computer model which have the capability to simulate cracking, yielding, all the nonlinear phenomena. So a nonlinear structural model is something which is you can say more difficult, more accurate compared to conventional linear model, and that model doesn't follow Hooke's law. It has the capability to tell the structural analyst that a particular element is yielded already during the analysis, or a particular element is cracked, or whatever damage that building can experience. So that model itself tells what damage is there at the end of the analysis. So you perform such an analysis for that much level of an earthquake which the client wants you to perform, and then the analysis results can be converted into any other damage. For example, if certain beam is cracked, you can directly calculate what repair cost can be expected from to repair that cracking. Or if a particular column or a shear wall gets yielded, you can convert that information into the repair cost. You can convert, there are models available which can convert structural responses into casualties, into number of injuries or deaths or downtime, into repair cost, right. So there are models available for that. So you will use such an approach to actually prove to the client that if this much an earthquake occur, this design is going to ensure that no one will get injured, and this process will actually be under the umbrella of this performance based design. And obviously at the end of this whole process there will be a peer review also. It's not that only one party or one firm or one expert will perform all that. There will be a third party review also, that is an integrated component of PBD. So there is no PBD without peer review, right. So you have to find a third party which is more expert than you, or at least equal, and then you have to submit everything to that group which validates or checks your all modeling, assumptions, analysis results and everything, right. So this approach actually allows you to try different things, and this is the way forward actually, because with growing urbanization, growing needs of infrastructural facilities, there is no other alternate actually if you think about the approach towards structural design. Because I give you one example that the traditional building codes, they are meant only for low rise buildings. Their design philosophy is mostly meant for low rise buildings. Now if you apply that design philosophy to a 50-story building, you may be completely wrong, right, partially or completely wrong, and the resulting design can be you can say very uneconomical. So in performance based design you will be free to try different alternate approaches different innovative structural forms and shapes, different ways to reduce seismic response, right, and then bring economy in your design. Conventional structural design is based on building codes, right. So, all structural engineers, they comply to that particular building code which have the jurisdiction at a particular location, at that particular site actually. So, performance based design is an alternate approach, right. One approach is that you follow the letter of the code and produce repeatedly the design for each building, for example, right. So, the design will be in that case will be the result of a cookbook type procedure, prescriptive procedure. For each building you follow the same approach, come up with the amount of steel and cross sectional size for concrete, for example. But performance based design will allow you to try different things. It will allow you to try any structural system which you can think appropriate for a particular high rise building. It will allow you to try different innovative materials which are not covered in conventional building codes, and innovative structural systems, for example, which are not covered in conventional building codes. It can also allow you to try different heights in different areas or locations of different seismicities, which might not be covered in a particular building code, right. So, it is an alternate approach. Conventionally, every building is designed following a building code, right. So, that is why I said that it is a new technology which you can, it can be considered a new technology which the conventional structural engineers can adopt, right. So, for existing design engineers, it is a matter of their capacity building. For new structural engineers like you, it is something which is the need of the hour, right. The main difference is that everything is quantified in a certain prescriptive framework. For example, I gave you an example yesterday also, that in order to account for geometric nonlinearity, currently the available computer programs, software, they can handle it with great accuracy, right. So, we do not need any specific code prescribed factors to account for p delta effects or all similar things, right. So, similarly is the case for material nonlinearity. He mentioned actually about response modification factor, but there are other factors also which account for different phenomena. Now, if you can explicitly account for that phenomena in your computer model can actually tell where will be the cracking, where will be the yielding, or where will be the crushing, then you do not need all that factors for your design, right. So, you can explicitly check whether the code's intention is fulfilled or not by using PBD. So, the general process goes like this, that you first start with conventional code based design. You follow, for example, ACI, ASE 7 or IBC, and then you come up with one design. Now, the conventional structural engineer will just finalize that design. This will go to drawings section and go to field, but the performance based design will be explicitly checking that design's performance. So, actually that initial design, that final design which the conventional structural engineer will finalize, will become an initial design for PBD. So, PBD will actually be started from that point onwards, that it will take that design, convert that design into a nonlinear computer model, because in order to construct a nonlinear computer model, you need all the finalized amounts of steel and cross section sizes and everything, right. So, because you have to tell the program that that beam will be yielded at that much moment, and you cannot tell that before finalizing the steel of that yield, that beam. So, the conventional design is finalized, then that design is used to construct a nonlinear computer model which can actually tell you the damage. then that computer model is subjected to dynamic analysis at different levels of earthquakes, and that model can explicitly tell that at what level you can expect cracking, at what level you can expect yielding, and at what level you can expect crushing, for example, right. So everything is clear. You can tell, you can actually show the results of that nonlinear analysis to your client directly, which is something which you cannot currently do now, right, because that model will itself be telling you that this much these beams will be yielded, or these columns will be cracked. So you can color code those elements within the software platform, and then you can directly tell the performance of your building to client, and if it is acceptable, design is okay. If it is not acceptable, change the design, do that again, and unless your desired performance objective is met, actually not your desired as a structural engineer, the desired from the client side, if it is met, then that design is final, right. And the last aspect was seismic hazard, especially the seismic hazard of Pakistan. I told you that the country itself lies on the boundary between 3 tectonic plates, which is actually a very complex seismotectonic environment, especially in the north and southern parts, and this have resulted in several devastating earthquakes in last 100 years, right. So we are you can say we are one of those unlucky countries which happen to lie on the plate boundaries, right, like Japan, like several of the other countries like West Coast US. So these kind of maps are called seismicity maps, which show the data of the past earthquakes. So each dot in this map is actually one earthquake which have occurred, and that dot is showing the location of epicenter, and the color is showing the depth of that particular earthquake. So these seismicity maps, or this data, actually becomes the basis of what we call as the probabilistic seismic hazard assessment, PSHA. So this process, PSHA, is the state of the art procedure nowadays. Previously we used to have deterministic seismic hazard assessment, DSHA, but nowadays we use this one. And within PSHA also nowadays there are several approaches. This actually, in one line, this is a process which accounts for, or basically it, in a probabilistic framework, it performs the analysis on all of the previous data available for a particular study area, and at the result of this analysis you forecast for future that what level of particular seismic hazard parameter is expected at that particular study area, right. So the ultimate result of this process is the hazard map, and hazard map is a map which shows the probability and level of expected future earthquake at a particular area, right. So you don't use these seismicity maps for structural design purpose, you use these hazard maps for the future design, and they may look like this. This map is actually taken from the Building Code of Pakistan 2007, and it was originally developed for peak ground acceleration values, and then based on different ranges of PGA we divided the country into 5 zones. So all you need to do is to know your zone. If you are designing a building here, you should know that which zone this site is located, and that information itself will be converted into the seismic loading, right. And obviously you will use a particular building code to convert this zone into the seismic loading. In this particular case it was UBC 97 or the Building Code of Pakistan 2007. So these kind of hazard maps give you an idea about what level of an earthquake you can expect at what location, right. Actually the seismic analysis procedure which was adopted in 2007 Building Code of Pakistan was taken from UBC 97 directly. So actually we needed a map which was exactly compatible with the definition of hazard used in UBC 97. So UBC 97 was meant for US, right? And in US they actually divided whole US into 5 zones, 1, 2A, 2B, 3 and 4, and actually zone 2 was divided again into 2 zones, A and B, based on the ranges of PGA, right? So exactly, since we wanted to adopt exactly the same procedure, which means that our seismic hazard map should exactly be compatible with the same definition, right? Because there is a Z factor associated with this zone. This zone is converted into a number, and that number is being used in calculations. So all of your calculations should be compatible with the seismic analysis procedure. So therefore this country also was divided exactly following the same procedure and in the same number of zones, right? So ideally, if you are doing it for first time, you could divide it into any number of zones, or even if there can be no need of zones also, you can directly show the PGA value on this map, right? So you can make PGA ranges. Blue color means 0.1 to 0.2, and whatever is blue is in this range, and then 0.2 to 0.3, 0.3 to 0.4, right? So actually there was ideally no need for this zonation unless you associate this map with a particular seismic analysis procedure also, which makes use of zones, right? So since this was the case in 2007, so we divided exactly following the same procedure. Now in the updated seismic hazard map, it is based on the distributed seismicity. It doesn't follow that zone concept. So and more importantly, it follows the spectral acceleration as the primary standard, the hazard parameter actually 2 spectral acceleration values, one at short period and one at long period. So in that map there is no zone. Directly we color code or provide contours for different values directly. So you can exactly get a particular value at different locations, right? Actually this question I will answer later in detail, but one of the prerequisites of performance based design, one possible prerequisites is the site specific PSHA. One PSHA is that you are doing it for big area, for whole city or for whole district, or maybe one whole country like this one, right? But there is a site specific PSHA also, which goes into more detail of that particular site only, right? Currently we are taking, like, it is all about resolution also. If you are doing something at a very high resolution, you are giving more importance to all the details, which means you are going more accurate, right? So site specific PSHA is also one of the things which should be performed before every important project, right? So if you are designing a 50-story building, ideally it deserves a site specific PSHA. I mean, if it is located somewhere here, let's say that 50-story building, so you should not directly rely on these numbers. You should go for site specific PSHA. I will have 1 or 2 lectures about PSHA also, right? So although I cannot make you expert in PSHA, I will just introduce this topic, so you can get an idea that what analysis we actually perform to finally come to this hazard map, right? Or actually hazard curve at each location, and which can be converted into this hazard map, right? So there are several of the outputs of PSHA process. One is this hazard map. The most common output is this one. So I'll give you an idea that what actually we do in that process, right? So you will have a clear picture, and ideally your point is correct that we need that historical data. Actually that whole process is based on the processing of that historical data that becomes the basis for future forecast. So if you can simply correlate this map with the faults and all the seismotectonic features, you can guess that there will be a fault here, you can guess that there will be a fault here, because all the historical seismicity we just convert that into future forecast, right, after all that statistical analysis in probabilistic framework, right. So I'll give you an overview of PSHA process also, right. So, the question was about site specific hazard assessment, and I was emphasizing its need. Currently, what is happening in our local context is that there are several very important structures which deserve this study, PSHA, site specific PSHA, but what designers are doing, that they are using code numbers and relying on that, right. So, sometimes the code number is high, and site specific PSHA tells that the actual level of seismicity may be less than that, and sometimes the code's number is low and the site specific hazard reveals that the actual level of hazard is more. This mostly happens in the vicinity of active crustal faults. For example, if you talk about this whole region which I am encircling, there are several active crustal faults in this region, but the overall number is zone 2B. But if you perform a site specific hazard assessment in the vicinity of a active crustal fault, you will get a higher number than 2B, right. So, depending upon the importance of a project, you should perform site specific hazard assessment. Similarly, there is another study which is one of the prerequisites of PSHA, and that is wind tunnel testing. In those areas where the wind loading can govern the design of the building, there is a special you can say separate study which is called wind tunnel testing, and in that you actually get a clear idea about actual wind loading which should be applied to your computer model from a wind tunnel test. So, there is a whole procedure for that. You make a small model of your building, you put sensors on that model and you put it in a tunnel, and that loading is that wind is applied to that model. And then there are several issues associated with wind loading also. Wind loading is more complex than seismic loading. For example, one of the issues is aerodynamic interference. Imagine that there is a loading which can be modified by the presence of nearby buildings, right. So, that aerodynamic interference is one of the issues in wind analysis, specifically dynamic analysis for wind. But seismic loading is simpler than wind loading. So, anyways, we covered some of the aspects of seismic hazard also in the context of Pakistan, and then lastly I summarized all of these aspects, converted into motivations for the development of performance based design.